Welcome back, focused learners, to today's Explainer. We're jumping right into one of the most absolutely fascinating challenges in computer science and linguistics. We're going to demystify how computers resolve grammatical ambiguity and learn to actually understand sentence structure. Get ready because we are diving deep into the incredible mechanics of statistical constituency parsing. To set the stage, let's kick things off with a classic quote from a Damon Runyon short story. He describes his character, Sky Masterson, as a guy who was willing to bet on any proposition whatever. Honestly, it didn't matter if it was a high-stakes card game or just some guy throwing a peanut from second base to home plate. The moral here for natural language processing is kind of profound. With enough knowledge and the right data, we can estimate the probability of literally anything. And that brings us to a really fascinating question, which is basically the core of our whole explainer today. If we can calculate odds for a card game or a weird sporting event, can a machine use math to essentially place a bet on the correct grammatical meaning of human language? Let's test this out with a deceptively simple phrase. Book the dinner flight. Now, for us humans, the sensible meaning is obvious, right? You want to book a flight that serves dinner. But a computer, well, it might seriously struggle here. It could just as easily interpret that sentence as a command to book a flight on behalf of a literal entity named the dinner, kind of like you'd say, book John a flight. We instinctively know that nonsensical interpretation is totally wrong, but a computer, it needs a hard mathematical reason to reject it. This just brilliantly illustrates the inherent messy ambiguity of human language. So here is our roadmap for today. We'll cover 1, the problem of ambiguity, 2, enter the PCFG, 3, finding the best parse, 4, where simple probabilities fail, 5, splitting the nodes, and 6, lexicalized parsing models. Section 1, the problem of ambiguity, a bug in language. The reality is, average sentences naturally have multiple syntactic structures. This happens all the time because of coordination ambiguity, like if I say old men and women, are the women old too? Or attachment ambiguity, like figuring out exactly which part of a sentence a prepositional phrase modifies. Because a single string of words can have dozens of perfectly valid structural interpretations, your standard rule-based grammars just don't cut it. We desperately need a mathematical solution, a probabilistic parser, to compute the likelihood of each interpretation and boldly choose the most probable one. Section 2. Enter the PCFG, probabilistic grammar. PCFG stands for probabilistic context-free grammar. Think of a standard grammar as just a rigid set of rules, like a noun phrase can be made of a determiner and a noun. Well, a PCFG is a system where every single one of those syntactical rules is given a conditional probability somewhere between 0 and 1. This number expresses the precise likelihood of a grammatical category expanding into a specific sequence. And here's the kicker. If you add up the probabilities of all the possible ways a specific category can expand, they have to sum to exactly 1. The whole shebang has to balance out mathematically. Section 3. Finding the best parse. Computing probabilities. Let's jump back to our earlier example, book the dinner flight. A PCFG calculates the total probability of a parse tree by multiplying the probabilities of every single rule used to build it. And this brilliantly illustrates the math at work. The sensible interpretation, booking a flight that actually serves dinner, yields a literal mathematical probability of 2.2 times 10 to the negative 6th. But the nonsensical parse, booking on behalf of the dinner, yields 6.1 times 10 to the negative 7th. That sensible parse has a significantly higher probability, so the disambiguation algorithm confidently crowns it the winner. But here's the catch. Computing every possible tree for long, complex sentences would literally take forever. To calculate this efficiently, parsers act kind of like a detective filling out a 3D matrix using what's called the probabilistic CKY algorithm. Imagine a grid where the algorithm looks at spans of words, say from position I to position J, and records the maximum probability of a specific grammatical constituent filling that exact span. By building this up piece by piece, from individual words all the way to the entire sentence, the computer efficiently tracks down the maximum probability parse without doing a bunch of unnecessary redundant math. Section 4. Where simple probabilities fail, mathematical blind spots. Real-world data from the switchboard corpus gives us undeniable proof that simple PCFGs completely ignore vital context. Just look at these numbers. 91% of noun phrases in the subject position are pronouns, like I or she. But in the object position, only 34% are pronouns, while a massive 66% are non-pronouns, like proper nouns. A standard PCFG just assigns one flat average probability to a noun phrase becoming a pronoun. It is totally blind to whether it's sitting in the subject or object slot of the tree. It assumes every rule is independent of its location, which is a major flaw. PCFGs also suffer from what we can call lexical blindness. Take a look at these two sentences. Workers dumped sacks into a bin requires verb-phrase attachment because into a bin describes where the dumping actually happened. But fishermen caught tons of herring requires noun phrase attachment because of herring describes the tons. A standard PCFG only sees the structural rules. It completely ignores the actual words. It fails to recognize that specific words, like the really strong affinity between the verb dumped and the preposition into, dictate entirely different tree structures. So to summarize the complication here, standard PCFGs fail for two main reasons. First, poor independence assumptions. They incorrectly assume every rule operates in a total vacuum, ignoring structural dependencies across the parse tree, like our subject versus object pronoun example. Second, a total lack of lexical conditioning. They completely ignore the actual vocabulary being used, meaning they can't use the unique syntactic behavior of specific words to resolve ambiguities. Section 5. Splitting the nodes. Parent annotation. Remember how the PCFG couldn't tell a subject from an object? We can actually fix this by splitting the nodes using a clever technique called parent annotation. Instead of just a generic noun phrase node, the algorithm tags the node with the identity of its parent. So, an NP under a sentence node becomes NP underscore subject, and an NP under a verb phrase becomes NP underscore object. By splitting these non-terminals, the algorithm can now track those structural dependencies and assign highly accurate, context-aware probabilities based on exactly where a phrase lives in the tree. It's a real game changer. Section 6. Lexicalized parsing models. Fixing blindness. But to truly give the algorithm sight, we need lexicalized models, like the famous Collins parser. These augment the grammar by associating structural rules with specific headwords and their part-of-speech tags. Instead of a rule just saying verb phrase, it says verb phrase headed by the verb dumped. This turns probability math into an intuitive balancing act that actually looks at the vocabulary to make decisions. But there is a catch. If you require exact word matches for every complex grammatical rule, you simply won't have enough data to calculate reliable probabilities, a notoriously tricky problem called sparse data. To solve that sparse data problem, the Collins parser uses a fascinating generative story checklist to break complex, heavily lexicalized rules into smaller, digestible probability estimates. Imagine the parser generating a phrase from the inside out. Step 1, it generates the head of the phrase. Step 2, it generates modifiers to the left of the head, one by one, multiplying their probabilities until it hits a special stop token. Step 3, it does the exact same thing for the right side, generating modifiers until stop. By breaking the rule into these independent, smaller steps, the parser can calculate highly accurate probabilities using the actual words in the sentence without running out of data. As we wrap up this explainer, we've journeyed from the messy ambiguity of human language to the elegant math of probabilistic context-free grammars, and finally, all the way to the sophisticated, word-aware logic of lexicalized models. But I want to leave you with a thought to ponder. We've seen how teaching a computer to basically bet on grammar requires careful mathematical modeling of structure and vocabulary. So how do these foundational, probability-based parsing algorithms eventually evolve into the massive, deeply context-aware AI language models we interact with today? Keep that question in mind as you continue your focused learning journey. Thanks for exploring with me.